Okay, so we have seen how first order linear differential equations can be solved, right? So we did some kind of a magic trick there. We managed to find this function I, and then we took the exponential of this and multiplied throughout, and then suddenly your equation, are transformed into a very nice perfect derivative. So we want to look a little deeper into what was going on here, and in this lecture we are going to introduce what are called exact differential equations, right? So, and the concept of an integrating factor is described in this lecture. Okay, so we have seen that the most general first order differential equation has this form, right? dy by dx is equal to f of x comma y, and so we have the freedom to write this as minus p of x comma y divided by q of x comma y. There is no loss of generality here, right? So only if you make these functions, particular functions purely of x and purely of y, which we did when we were looking at separable forms, then you're making a concession. But at this point it's completely general, right? So this allows us to recast this first order differential equation in this form, p of x comma y dx plus q of x comma y dy equal to 0, right? So this equation is as general as the first equation itself. So this is a general first order differential equation. Now, so we will introduce the notion of an exact differential equation. So we would call this differential equation as exact if it is something that can be obtained from some function of x comma y. So if we are able to find some function f of x y such that the derivative of this function, right, the differential of this function, right, which we know is involves these partial derivatives. So since f is a function of both x and y, so if you take the differential of this f, it's given by dou f by dou x dx plus dou f by dou y dy, right? So you see that the left hand side has some function times dx plus some other function times dy, right? If it so happens that this left hand side can be obtained as the exact differential of some function f, then we say that the differential equation is exact, right? If a differential equation is exact, this means that it can simply be written as df equal to 0. Now the left hand side is an exact differential, so immediately what it implies is f of x comma y equal to constant, right? So which is nothing but the solution for the problem itself, right? So if such a function exists, then if you can somehow find it, then that solves the problem immediately, right? If f of x comma y equal to constant is the solution. Now of course it would be nice to to tell immediately as soon as you're given a differential equation, is it already exact, right? Is there a prescription to find out whether it is exact? And so the answer is yes, right? So the condition is the following. So we are saying that there is an f such that df is equal to this. So p of x comma y is equal to dou f by dou x, and q of x comma y is equal to dou f by dou y. So if a differential equation is exact, then if you take the y derivative of p, then you get dou p by dou y, and if you take the x derivative of q, then you get dou q by dou x. And immediately we see that both of these must be the same because they are both the second derivative of f with respect to x and y, the partial derivative dou squared second derivative dou squared f by dou x dou y, and therefore dou p by dou y is equal to dou q by dou x, which is necessarily true if your differential equation is exact, right? So this is a necessary condition for your original differential equation, right? So when you're given a differential equation, you don't know what f is, whether there is such an f or not. But if you can immediately test, with this, if you're able to test this, then if your differential equation is exact, this must hold. But it turns out, in fact, that this is even stronger. There is also a sufficient condition, right? So what we can show is that if you're given a differential equation, if you start with a differential equation like this, some arbitrary differential equation, and if your if you're also able to show that if you can explicitly see that dou p by dou y is equal to dou q by dou x, then for sure there exists a function f of x. We can construct a function f of xy such that p of x comma y is equal to, it's a the differential of this f will give the left hand side basically. So you will be able to construct an f of x comma y such that p of x comma y is equal to dou f by dou x and q of x comma y is equal to dou f by dou y. So integrating, so how do we see this? So integrating this first equation. So let's say yeah, we are looking for a function f of this kind. So let's write down this equation and then integrate both sides. So we have f is equal to integral of p dx plus, you know, some, you can put, instead of a constant, you can actually put an arbitrary function of y, right? Because all you need is the partial derivative of this function with respect to x must give you p, and that it will do no matter what function of y that you choose here to add to this. Now, but this function itself must be something that you should be able to determine from some independent constraint, and it should be compatible with this other constraint. So that's what we will show holds, you know, provided this condition holds, right? So we will show that next. So what do we want to do? We want to be able to, you know, impose this constraint q of x comma y is equal to dou f by dou y. So let's just take a derivative throughout with respect to, partial derivative with respect to y. So I have dou f by dou y is equal to dou by dou y of integral p dx plus d gy by g of y by dy, right? Because the partial derivative of g with respect to y is the same as the total derivative of g with respect to y. So I have d, rewriting it, I can write it as d by dy of g is equal to dou by dou y of integral p of x comma y dx minus dou f by dou y is the same as q, right? Because this is something that we already have. It's an essential, you know, it's a condition which we already imposed. So I have minus q. So now you look at this equation carefully. So on the left hand side we have the full derivative, the total derivative with respect to y of a function which is a, you know, pure function of y. So the derivative with respect to y of a function which is purely a function of y must be another function of y. It cannot have any x in it. But on the right hand side you have, you know, some complicated stuff. You have a partial derivative with respect to y of a function p of x comma y which is integrated with respect to x, dx, and then you have a minus q of x comma y. But the only way that this would be, you know, a compatible equation if the right hand side turns out to be purely a function of y alone. In other words, there can be no dependence on x of this combination on the right hand side, right? So, you know, another way of stating this is if you can find the partial derivative of the right hand side with respect to x and show that it is equal to 0, right? So let's find the partial derivative of the right hand side with respect to x, right? So if that happens, then of course g of y can be just integrated, right? If the right hand side is purely a function of y, then we can just solve for g of y in terms of this integral, you know, with respect to y, and then you're done, because f is, you know, this integral, p is known and g is known according to this prescription. You have managed to work out a formal expression for this function f in terms of p's and q's, so you're done, right? So, but there is only one block in the way, and that block is that we must ensure that this right hand side must be purely a function of y, and that we will now argue is actually true. In order to do that, we will take the partial derivative of the right hand side with respect to x. We have dou by dou x of dou by dou y of this integral p of p dx minus dou by dou x q, but then I can, you know, exchange these partial derivatives. So dou by dou x integral p dx will just be p, and then I have dou p by dou y minus dou q by dou x, but this is equal to 0 because we are given that, you know, your original differential equation satisfies this condition. Dou p by dou y is equal to dou q by dou x. So basically we have managed to show this integrand which goes into this, you know, computation of g of y is purely a function of y, right? Because its partial derivative with respect to x is 0, and therefore this is a completely legitimate operation to do, and you will get a function, in y, and that you use to get your, function f of x comma y. Therefore, you will be able to. So we have explicitly shown how, given this condition, dou p by dou y is equal to dou q by dou x, it's going to imply that your original differential equation is exact. So it works both ways. It's a necessary and sufficient condition for your differential equation to be exact, right? So a quick word about, what we were doing for the ODE, the first order linear differential equation, was actually we were finding something called an integrating factor. So not all differential equations are going to be exact, right? So in fact, you have to verify if it's exact or not. But using this technique we have to find whether dou p by dou y is equal to dou q by dou x. And so in fact, the vast majority of differential equations you might encounter will not be exact. But there is this, what we showed for linear differential equations is that there is of first order is that there is a prescription by which you can multiply throughout, and then the differential equation becomes exact, right? So the equation, so let me, before we go to first order differential equations and view it from this point of view of integrating factors, let's just quickly look at a few examples of what integrating factors are, right? So integrating factors are factors with which you multiply a differential equation and convert a non-exact or inexact differential equation into an exact equation. So let's look at this very simple example. So x dy minus y dx is equal to 0. So this differential equation, of course, you can solve it, right? But that's not the point here. So if you look at this differential equation, it's not exact. Why is it not exact? If you take the yth derivative, or you'll get a, you can take the yth derivative of this term and the x derivative of this. One of them will be 1 and the other one is minus 1. So it's not exact. But on the other hand, if you multiply throughout with 1 over x squared, it's going to become 1 by x dy minus y by x squared dx, and you can explicitly write this down as the derivative of y by x, and this is equal to 0. So now you have managed to convert an inexact differential equation into an exact differential equation by multiplying by this factor 1 over x squared, right? So therefore the solution immediately follows, right? So the factor 1 over x squared is called the integrating factor. So let's look at another example. If you are given some differential equation and it has this form f of x dx plus g of x h of y dy equal to 0, with none of these functions identically 0. If you ask, when is this differential equation going to be exact, right? So the condition is this dou f by dou y must be equal to dou by dou x of g times h. But f is purely a function of x, so that the left hand side will vanish. So this implies that the right hand side must be equal to 0, but the right hand side itself can be simplified. You can write it as dg by dx times h of y equal to 0. Now h of y itself cannot be 0 because that's given in the question, and therefore it implies that dg by dx equal to 0. So this equation is exact only if g is a constant. It cannot have any more non-trivial dependence on x. If it's a constant, then this overall differential equation will be exact, right? So in this lecture, the focus of this lecture was to define what are exact differential equations and to tell you what integrating factors are, right? So, and to also just give you a hint that we have already used integrating factors in some clever way, with first order ODEs, linear ODEs, where we found this mysterious factor e to the I, and when we multiplied throughout with e to the I, the equation was actually going to become exact. But we will discuss a little more about this ahead, but that's all for this lecture. Thank you.